Hello everyone. In this lecture, we'll be seeing the fifth properties of function. It is the formula for inverse of composition of functions. So if I have a map f from A to B and g from B to C, we already know that it is possible to define g composition f from A to C. Suppose if both the functions f and g are invertible, observe that it is possible to have a inverse function f inverse from B to A and g inverse from C to B. It is possible to define the map f inverse composition g inverse because the domain of f inverse, which is B, is equal to the codomain of g inverse, which is B. So we are going to state that this map F inverse composition G inverse will be the inverse of the map G composition F. This is what we are going to show in this property. So to prove this one, we know that f is an invertible function. So we'll be having f inverse from B to A, and we are well known with this condition now. If I multiply f inverse at first, I'll get IA, that is domain of f identity map. And if I take composition in the second place, I'll be getting identity map of f codomain B. So similarly, g from B to C is invertible. So we'll be having a inverse function g inverse from C to B, which satisfies this condition. Since if we take composition g inverse at first, we'll get identity map on domain of G, that is IB. If we take g inverse in the second place, then we'll get the identity map on codomain of G, which is IC. Now, we already know that G composition F from A to C is possible. We are going to define one function H, F, that is nothing but F inverse composition G inverse from C to A. We already know that F inverse, it is a map from B to A, and G inverse, it is a map from C to B. So it is possible to define F inverse composition G inverse. So here domain of F inverse and codomain of G inverse will be equal. Now I am going to show that this H is the required inverse of the map G composition F. That is G composition F, the whole inverse. So if we want to show that a particular map is a inverse of another one, the condition is if we take that map composition at first, we have to get the domain identity map. So we have to get IA. If we take composition in the second place, we have to get codomain identity map, that is IC. So these two conditions are necessary to prove. So let us take the first one. H composition, G composition, F. So here we know that H is nothing but F inverse composition G inverse. We are taking this one composition with G composition F. Already we know that composition of functions is associate. So I am going to change the bracket. F inverse composition, G inverse composition G composition F. Also, we know that G is a map from B to C, and since we are taking composition of G inverse in first place, we will be getting identity map on the domain of G, that is IB composition F. So let us take, without loss of generality, I am going to take the composition of first two maps. F inverse is a map from B to A, and IB, it is a map from B to B. So it is possible to define F inverse composition IB because the domain of F inverse, which is B, is equal to the codomain of IB, which is also B. So if we take composition with the identity map, we'll get F inverse. So the remaining one is composition with F. So observe that F inverse has been taken composition in the first place. So we will get the domain of F identity map. So it is IA. The first condition we have proved. Similarly, we are going to prove the second part. Now let us compute G composition F H. That is taking composition of H in the second place. So G composition F composition H will be equal to G composition F. Let us substitute the function H, which is F inverse composition G inverse. Since composition of functions is associative, we can change the brackets. So G composition, I am going to first apply the composition for F and F inverse. So since F inverse, it is in the second place, we'll get the identity map on codomain of F. So it is G composition I, B composition G inverse. So without loss of generality, I can apply the composition for first two functions. G is a map from B to C and IB is a map from B to B. So it is possible to define decomposition IB since the domain of G B is equal to the codomain of IB, which is B. So since we are taking composition with the identity map, we will get the same map. So G composition G inverse. Observe that G inverse is in second place. So we'll get identity map on the codomain of G and the codomain of G is C. We'll get the IC, identity map on C. This is the second condition we have to prove. So since both the composition gives the identity functions respectively on IA and IC, we can conclude that this H, that's nothing but F inverse composition G inverse, will be the inverse of G composition F. So we can conclude G composition F, the whole inverse is nothing but F inverse composition G inverse. So this is what we have to prove.